Good day, I'm Norman Wahlberg. Today we're going to do something rather interesting. We're going to take this particle-antiparticle symmetry that comes from physics and extend it into mathematics. This is going to be essential for us to be able to use the multi-set framework consistently across the board to set up linear algebra, field theory, and other things as well, including group theory later on. So in some ways what we're going to do now will appear like a game. And you can think about it that way. It's a kind of a technical device that we're going to introduce that allows us to make sense of things that we want to write down. But because we're obligated to be very precise about what things actually mean, we actually have to identify the objects that correspond to the things that we want to write down. So the story is motivated by this remarkable discovery of 20th century physics, going back to essentially Dirac around 1930, that there was some kind of strange antiparticle for an electron, which subsequently was called a positron. And then eventually physicists realized that this was not some kind of isolated occurrence, but was rather a manifestation of some kind of general symmetry, that basically every elementary particle has an associated antiparticle with roughly the same mass but opposite charges. So not only do we have an electron positron, but we have a proton and an antiproton, a neutron and an antineutron, a neutrino and antineutrinos, up quark, anti-up quark, and so on. And generally the convention that the physicists like to use is that if the particle is, just say, denoted by a V, then the antiparticle is denoted with a V with a bar over it. So there's at least theoretically some kind of symmetry between these particles and antiparticles that was discovered by physicists. And now I think they have some kind of reasonable explanation for why this sort of goes across the board. So it's very interesting, and we're going to take on board a little bit of that understanding from the 20th century physicists. So to motivate this, let's recall that one of the important things that numbers do for us is that they allow us to scale existing data structures. That means that we can multiply, say, m sets by numbers. So for example, here is a rather general m set. So I'm not being very specific about what objects are in here. These could be any kind of mathematical objects as long as we've already have a prior definition of what they are. We'll just represent them as some kind of objects, say heart, heart, diamond. And we want to take this m set and we want to multiply it by 2. So here is the number 2, represented by our two little marks. Okay, and we know how to do that. We multiply each one of these marks by each one of these things, and the basic rule here is that, well, a mark times a heart is a heart. So we have a heart, and then we have another heart. And then we go to this one, a heart, and another heart. And then a diamond, and another diamond. And so that's the way we multiply this m set by this number. And a special case is what happens when we multiply the same m set by the number 0, or the empty m set. Well, in this case, there's a lot of products of the form emptiness, or nothing times something, and nothing times something is nothing, so we get nothing on the right-hand side, so we get the empty set again. So this empty set is playing a very generic role here. It's really just the empty, I should say empty multiset. It's the empty multiset, which can be a number, it can be a natural number, it can be a negative number, it can be an integer. We can even think about it as being a type of m set of pixels or maxels and so on. So it's a rather general kind of thing that plays its role in many different situations. So now we know how to define n times a if n is a natural number and a is an m set, and there's a pleasant algebra. Okay, now we want to ask this question, this natural extension: how do we multiply an m set a by a negative number? How does that work? Well, it all comes down to specifying what happens when we multiply some generic object by each of our three sort of basic ingredients of numbers, namely the mark, emptiness, and the anti-mark. And we've already convinced ourselves that the mark times, say, heart ought to be heart, and that nothing times heart ought to be nothing. So now the question is, what should anti-mark times heart be? Let's temporarily call it heart bar. So we're going to introduce possibly a new kind of object called heart bar, which is the result of taking our little anti-mark and multiplying it by heart. Okay, these three rules will then tell us how to multiply our basic elements with a general generic object. And that will then allow us to extend our multiplication of numbers times m sets to a very general situation. We'll now be able to multiply any number, be it a negative number or a natural number, by an arbitrary m set. Okay, so what about this new object that we're introducing? Well, it has to have a very special property. So we require that this new object, heart bar, have the property that it cancels with heart. That heart together with heart bar gives us nothing. And this is an equation that has to happen inside an m set. So, if we have an m set and it contains a heart somewhere and it also contains a heart bar or an anti-heart, then those two things are going to cancel just the way a neutron and anti-neutron cancel, and the result is nothing. So that's the property that this new object has to have, that it has to cancel with this one. And why is that? Well, the reason is the following. That if we take 0 times any m set, we should get 0, or the empty m set. And so if we take the empty m set and we multiply, say, by the single m set containing just a heart, whatever that might be, then we know we should get an empty m set. But we also know that this empty m set, or the number 0, is in some sense the same as the m set consisting of a mark and an anti-mark together, because we know that that mark and the anti-mark cancel to give us emptiness or nothing. So what would happen if we considered this product here by the usual rule? So we just multiply the mark times a heart, here it is, and we multiply the anti-mark times a heart. Now we know that the mark times a heart is heart. And so, well, we're going to get this new m set is heart, and then the other one is anti-mark times heart. Now, this supposedly is going to be the empty m set. So for this to work, we require that this new object, anti-mark times heart, which is what we're calling heart bar or anti-heart, that object has the property, this cancellation property, that when we have a heart and this anti-heart together, they better cancel to give us the empty m set. In other words, inside the m set, we want this crucial cancellation that heart times heart bar is nothing. So we're really proposing something that's quite dramatically new here, even though it's a little bit formal and technical and maybe sort of out of the vision most of the time. But nevertheless, theoretically, it really changes the landscape of mathematics. So I remind you that our basic premise is that we are going to build up mathematical objects from the bottom up. Right? That's our basic orientation. We're starting at the bottom, not already assuming all kinds of stuff, and we're building things up step by step, one at a time, and going from simpler structures to more complicated structures to more complicated structures. And now what we're proposing is that we're going to have this general orientation that for any bona fide mathematical object heart, so at some process in this building up, we get some object that we're very comfortable with, let's call it heart, okay, that we're going to propose that there is another object, kind of a mirror object, or actually an anti-object, that corresponds to that object, which is its anti-object. In other words, there's going to be a new object, heart bar, which we can define as the anti-mark times the heart that we're considering, that has this crucial cancellation property that we've seen several times. So we want this to be true across the board. in the same way as the particle-antiparticle duality works across the board for elementary physics. It's not just an electron and a positron or a proton and antiproton. This is a general kind of symmetry that's going to apply to any kind of legitimate mathematical object that we're able to construct. And some definition or terminology. So if, let's say, the object that we're considering happens to be the object called heart, then we'll call this thing here anti-heart. And we'll say that anti-heart is the anti of heart. So I'm introducing this usage of this word in a slightly different way. So this is supposed to be similar to the use of the word opposite. The opposite of black is white. The opposite of day is night. Now we're going to talk about the anti of a mathematical object, heart, as being this thing here, anti-heart. Or we'll say heart bar when we sort of talk about how we write it down. So the anti of a mark is the anti-mark. The anti of the anti-mark, how do we get that? Well, the definition is always the same. The anti of something is what you get when you take the anti-mark and multiply it by that something. In this case, we know what we get. We take the anti-mark and we multiply it by the anti-mark. Anti-mark times anti-mark. We've decided already that that's going to be the mark. So this crucial property that the anti of the anti-mark is just the mark. So I do admit that this takes some getting used to. It may take a little while for this to sort of sink into our consciousnesses. But it's pretty interesting. And we're going to see that it's really essential to be able to do the kinds of things that we want to do. So what is this anti of something? Is the anti of a number just its negative? No, it's not. Okay? The anti of a number is not its negative. The anti of a number is a new kind of object. So for example, here is the number that we usually call 4. It's an M set with a mark, 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 mark in it. It's a natural number. So the anti of this thing, what is it? Well, this is a mathematical object, and its anti is what you get when you multiply it by anti-mark. And by definition, that's just a new object that has a bar over it. Okay, so it's not as if we really do anything. We just take that object and we put a bar over it, and then it's some new object, the anti of what we had previously. So there's the object there, and notice that the bar goes right over all of it. So we're taking the bar of the whole thing. And if we were going to write this as a Hindu Arabic numeral 4, then we would just talk about 4 bar. And what kind of a new thing is this? Well, it makes sense to say that this type, the type of this thing is anti-nat. This is in nat, and so this is in anti-nat. And what property does this have? Well, if we take an M set consisting of this and 4 bar, so there's 4 and there's 4 bar, or anti-4, then those two things are going to cancel. That's the basic cancellation. And I'm going to get the empty set, or 0. On the other hand, minus 4. Okay, minus 4 also involves anti-things. But minus 4 was the M set consisting of 4 anti-marks. Anti-mark, 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 anti-mark. That's a negative number. That's actually quite different. So this is different from this. If you like, here the bar extends over the whole thing, and here we're just having the individual elements inside the M set being barred. So this is not equal to this. They're different. So for example, if we make an M set containing the number 4 and the number minus 4, then we're not going to get 0. We're not going to get the empty M set, because these two things don't cancel themselves out as objects. This is now a new M set, which has 2 elements in it. One of the elements is 4 and the other element is minus 4, and that's just what it is. It doesn't simplify to anything simpler. But if you have 4 and anti-4 in it, you are obliged to cancel those object-anti-object pair and simplify. So let me give you some motivation why we want to do this. So anti-objects allow us to introduce negative numbers into vexils and maxils. Here, for example, is a vexel. It is an M set consisting of singletons. The singleton 0, the singleton 0, the singleton minus 1, the singleton 1, the singleton 1, the singleton 1. Okay, so these are singletons from integers. That means they are lists whose elements are integers, but just a list with one element. And we know that we can represent this kind of thing in a sort of a vector form by recording the number of zeros we have, the number of ones we have, and the number of minus ones we have. And we could write this down in a Fries kind of fashion like that, with this convention that the 0 spot is identified by some bars, so we know where it's sort of centered. Here's another kind of vexel, but now this is a new kind of object, because it has not just singletons, but also some anti-singletons. So let's try to get our heads around this. Okay, what do we see in this M set? Well, how about 0 singletons? How many 0 singletons are there here? Well, there's not really one 0 singleton. There's minus 1 singleton, because this anti-singleton 0 counts as minus 1 of them. That's what we're going to do. We're going to interpret this anti-object as minus 1 of the original object. So we see that there's one anti-singleton 0 here, so we're going to record that with putting a minus 1 in the 0 spot. In terms of minus 1 singletons, there's 2 of them, so we'll put a 2 in the minus 1 spot. And also in the 2 spot up here, there's a singleton 2, only one of them, so we'll put a 1 there. But in the singleton 1 spot, we have singleton 1 bar and singleton 1 bar that corresponds to minus 2 singleton 1s. So we would put a minus 2 there. So let me try to convince you that this actually makes sense, that this is consistent, this is logical. Because suppose we wanted to add these two vectors. Okay, these are M sets, so we know how to add M sets. We just put everything together. So V plus W, so we take all of these elements and just put them in there, and then we add all of these elements, starting from here, there we go. Okay, so now we have this big M set. And now we look at it and say, well, wait a minute. There is a singleton 0 here, and there's its anti-object. In fact, there's the anti of this. So this thing and this thing cancel. Poof, they're gone, replaced with nothing. And now there's only this singleton 0 singleton left. How about minus 1s? There was minus 1 singleton there, and there's another one there, and another one there. So altogether there's 3 of them. How about 1 singleton? So there's 1 here, and 1 here, and 1 here. But here there's an anti of one of these, and here there's another anti of one of these. So this anti cancels with one of these. We don't really care which one. Say this one here, they cancel. This one cancels, say with another one, say that one there. And we're left with a single singleton 1. And the singleton 2 is along fine, so there it is just there. And then when we count what we have left over, well, we have 1 singleton 0, we have 3 singleton minus 1s, and we have a singleton 1 and a singleton 2. And we see that this is indeed what we expect in terms of component-wise addition of these vectors over here. So there's the 0 spot, so 2 plus minus 1 is indeed 1, 1 plus 2 is 3, 3 plus minus 2 is 1, and 0 plus 1 is 1. So these minus 1s here are representing these anti-objects, and they add to the original objects in the right way, namely they cancel with them in the multiset. So we get the correct additive structure on the vector side of things. The price that we pay is that in order to have minus 1s, where we want to interpret those minus 1s as multiplicities, we're going to interpret them as being multiplicities of anti-objects. I guess it goes back to, the question of what is minus 3 cows? What does it mean to take 4 cows and add minus 3 cows? Well, it's hard to do that physically. You have to imagine a minus cow as some kind of fictitious object representing some debt. It's not really the same as a tangible physical cow, but it's a debt. It's some kind of virtual object. That's sort of what we're doing here. We're being more precise about these virtual objects and giving them names and these bars over them. Basically, we're doing the same kind of thing. 4 cows plus minus 3 cows gives us 1 cow. 4 objects plus 3 anti-objects give us 1 object of that particular kind. So here's another example of how we can use this concept for something that's very important for us, which is to develop Maxwell theory in a kind of a very good arithmetical way. So here's an example of a new kind of Maxwell. It's got pixels in it, but some of the pixels are kind of anti-pixels instead of regular pixels. So we have minus 1, 2, and there's a couple of them. We have a 0, 1, but that's an anti-object. We have 0, 2, 2 of them, and then we have 3 of these anti-1, 1 pixels. Okay, so this is a Maxwell with both pixels and what we might call anti-pixels. It's obvious what we mean by that, right? That's an anti-pixel. That's a pixel. Okay, and we can represent this thing now, and here's our integral screen. Okay, representation. We have our lines like this. There prominently in the middle is our 0, 0 spot. That's the basic reference frame. Okay, so we put multiplicities here. So minus 1, 2, that's minus 1, 2. So that 2 there represents these 2 fellows here. This 0, 1, so the 0, 1 is that position, but we don't have 1 of them. We have basically minus 1 of them because there's an anti-0, 1 pixel there, not a regular 0, 1 pixel. So we put a minus 1 there. That minus 1 is a representation of the fact that we have an anti-pixel there. We have 2 of these pixels, the 0, 2 pixels, so we put a 2 there. And then we have 3 of these anti-pixels, so we put a minus 3 in the 1, 1 position. So this is a representation of this M set, which contains both pixels and anti-pixels now. And it's very important for us to be able to do this, because we want to do arithmetic with Maxwells. But we for sure want to have integers in the Maxwell positions. So we basically want to do standard linear algebra. We don't want to just restrict ourselves to natural number entries in all our matrices and vexels because we're always thinking in terms of them as being M sets. And if they were M sets, then the multiplicities would always have to be positive. So we want to free ourselves from that, and that's exactly what we've done. We've enlarged our point of view, admittedly by introducing these strange new anti-objects, but now we're in a position to interpret very precisely what something like this means in a multi-set framework. Right, so these numbers are still representing multiplicities of objects. Now, in certain areas of mathematics, somewhat more sophisticated mathematics, negative numbers of objects are introduced by what are sometimes referred to as formal linear combinations. So for example, in group theory, maybe you have a group, a finite group, and it has elements G1, G2, G3, G4, and so on. In some situations, it's useful to consider linear combinations of these things. For example, we like to do arithmetic with combinations like 3G1 minus 2G2 plus G3. And it's a legitimate question to ask, what exactly are we talking about here? And in traditional algebra, there's a little bit of dodging and weaving when it comes to saying exactly how one sets up such formal combinations. One usually does something like this and says, well, we're considering some formal combination and so on. So what we're doing here is trying to be more precise about what's really going on when we consider a formal object like this. What we're proposing here is that this thing here is really probably living in a multi-set framework. Okay? We're talking about a multi-set, really. That's what this represents, where there are 3 G1s, a single G3, and 2 anti-G2s. If we have the notion of an anti-object, that makes perfect sense. And then we have a consistent multi-set interpretation of this kind of formal combination. That's going to be useful in quite a lot of contexts. So this object anti-object setup is an alternative to some more loose kind of discussion that often one finds in advanced algebra courses. Now, a curious aspect of the 20th century physicists' understanding of particles and antiparticles is that although there's this theoretical symmetry, practically, if you look out there in the real world, you do not see a symmetry between particles and antiparticles. Pretty well everything in our ordinary world consists of just particles, and the antiparticles of the things in our world are very hard to find. That's why they weren't observed until 1930. So there's definitely an asymmetry with regard to the prevalence of particles and antiparticles, at least in this neck of the woods where we are here in our universe. Okay, so similarly, we're going to find that we're going to use anti-objects rather minimally. It's not as if now suddenly our mathematics is going to be populated by all kinds of anti-things. Rather, this is a sort of technical device that allows us to justify putting negative numbers in lists that are multiplicity lists for M sets. So it's a way of still doing our arithmetic, but in a more general way, in a kind of a formally correct way. Because we're going to be rather general about being able to take an anti of something, it might be that the objects, like heart, that we're considering might be actually quite long objects. We could be considering an M set with 3,000 things, and we might want to take its anti. So we'll use this notation that anti-mark times heart is heart bar, with the bar right over the heart. But sometimes we will also allow ourselves this alternate usage where we put the little bar to the right, almost like an index. Okay, so you can imagine if this is some big M set that's very long, we'll just stick the bar at the end, sort of at the end of the final bracket, just so we don't have to write some big overline. So for example, here, this is an M set. It's actually a maxil. It's got 3 pixels. So it's possible for us to consider the anti of a maxil. And instead of writing this, we could alternately just write the maxil with a prominent bar at the end on the right as an index there. So that means the anti of this maxil. So in our next video, I do want to say a little bit more about this anti operation. It's obviously a kind of a novel and interesting thing, and there's a few more things to say about it. And then after that, we'll get on to some very interesting applications to, setting up field theory and higher arithmetic, really, from the Maxwell point of view. But next time, a little bit more about this curious anti-operation that we've now introduced into mathematics. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.